Hello, my name's Paul Hammerton and I'm a lecturer in mathematics at the University of East Anglia in Norwich. Now, mathematics has lots of different branches. Some people are more interested in what we would think of as pure maths, understanding the structure of maths, theorems, proofs, things like that. My great interest in mathematics and what gets me excited is how I can apply mathematics to the real problems that we see around us. And that's an aspect of maths that we often refer to as mathematical modelling. And I'll begin by just introducing two particular fields that I've looked at and used my expertise in mathematics to do research on. So the first thing is sonic booms. So that's when an aircraft is travelling faster than the speed of sound and it generates pressure pulses, as we see here, with an increase in pressure with time, then a slow decrease, and then a sharp increase again. So you hear that as like two whip cracks. Another problem is the idea of solitary waves, where we've got a single pulse of a fluid and that's moving along. So famous experiment on the left of generating one of these big solitary waves, we call it, which propagates down the canal. So solitary waves or solitons. And these two fields have got something in common as far as the method we use to solve them. So the real topic of this talk is, why do we need hyperbolic functions? A new type of function, probably most of you won't have seen these functions. You've seen sines and cosines, trigonometric functions. These are a slight modification of those. And we're going to see how these appear in real problems. So first of all, what do we really mean by mathematical problem modelling? Well, first of all, we've got some practical problem and we want to predict an outcome. Now, I'm very interested in sport, so some of the examples in this talk are going to be drawn from sport. So it might be a golfer hits a ball at a particular angle with a particular initial speed, and we want to know how far the ball travels. So that's the outcome that we want to predict. Now, that's a really pretty complicated problem. So we always begin by trying to simplify the problem and finding a first model. So we've got some model, we find equations that describe that problem. Then we solve the equations and get a result. So maybe for how far the golfers hit the ball. And then we compare it with actual measurements from experiment or observation. Typically, it's not going to be that great an agreement, because we've simplified the problem a lot. So then we think, what effects have we ignored? And can we incorporate those into our model and so get a second model? Then we do the same thing. We're going to solve the new set of equations and we then compare with experiments and hopefully the comparison has improved. We're getting a better estimate of the result we're looking for, like the range of the ball. So here, distance the ball travels, it could be a golfer. Obviously, it's going to matter a tremendous lot exactly how far the ball travels in order to clear the pool and also clear that bunker just in front of the green. In baseball, batter trying to hit the ball out of the stadium for a home run, the distance of change of distance of 2 or 3 metres is going to make a massive difference to the game. So the problem we might be looking at is, given an initial speed and angle from the horizontal, can we find the path, or we sometimes call it the trajectory, that the ball takes? And probably the easiest thing to allow a comparison between theory and experiment, or the real world, is the horizontal distance travelled before the ball hits the ground, the range. So in this particular case, we've got this is the range. So the range is just over 90 metres. So we would then compare that for the same angle and speed, the same angle of projection and speed, and compare that estimate with real life. Now, that's actually quite a complicated problem and not something we can easily do in 15, 20 minutes or so. So let's just have a look at a slightly simpler problem. We're going to look at the speed of a golf ball dropping vertically. Now, we know the reason. We're going to drop it from rest at a particular height. The ball's going to fall due to the effect of gravity. And what we really want is an equation that gives the speed and the distance fallen as a function of time. So thinking about our order of things in our modelling, the first simplification is that we're going to assume that gravity is the only force acting. Big simplification. So, if gravity is the only force acting, acceleration is constant, and so the speed or the velocity is given by the acceleration due to gravity multiplied by time. I've got a bit of calculus in there, but I'm skipping over that. So we've got that V equals G times by T, where G is about 9.8 metres per second squared. So we plot that. V equals GT, we get our green line, and then we compare with experimental measurements. So compare the theory with experimental measurements for different sorts of balls, a tennis ball, a golf ball, something like that, a baseball. So green was our theory, blue and red are our experimental measurements. And we see that to begin with, round here, we've got pretty good comparison. This is speed up this axis. This is our V here and T here. See, good agreement when T is small. But then the results diverge quite a lot. And what do we notice? We actually notice that the velocity is tending towards a constant. And we call this the terminal velocity. Now, in our live interactive session, we'll have a bit of a chat about what factors actually affect the terminal velocity. And more to the point, what have we actually ignored in our initial model, where the force, the only force, was the weight, the effect of gravity. I think most of you realise that we're going to have some air resistance. So we're now, next iteration, is we're going to build in some air resistance, or a drag force. Now the drag increases with speed. I think that's a sort of natural thing to understand. But in fact, experimental measurement, theoretical investigation shows that in most cases, the magnitude of the drag is proportional to the velocity squared. So you write D equals kv squared, where k is a positive constant. Now, at the terminal velocity, that means there's no acceleration. So what we've got is that the drag force is equal to the force due to gravity. They balance out. So we've got our drag force equals our weight, and we rearrange it to get our expression for the terminal velocity. And you can see from this, again, it makes sense. If the drag is very small, k is small, then the terminal velocity is going to be very high, and vice versa. And we'll discuss what factors come into determining what k is in our live discussion. So we now ask, how does the velocity change with time? As it increases from 0, it's dropped from rest, up to the terminal velocity Vt. We find that this involves hyperbolic functions, this new class of functions that I mentioned earlier. So we're now, before we return to this problem, just going to have a quick look at what hyperbolic functions are all about. And hyperbolic functions are defined in terms of the exponential function. And I think most of you will have seen the exponential function. E to the x, where E is this fundamental constant, 2.71. And the most important property of the exponential function is if we differentiate the exponential function, we just get the exponential function. So that's a very important property, the only function that has that property. And we're going to use that. So first of all, just a little bit of a plot of an exponential function. We can see that because it's e to the x, and e is a positive quantity, e to the x is always positive. And then the fact that the derivative is also equal to exponential of x, the slope of the curve is always positive. And so we get a picture that looks like this. That y, when x equals 0, y equals 1, and then it increases as x increases. So now the definition of these new hyperbolic functions in terms of exponentials. So we've got the hyperbolic sine of x is just half e to the x minus e to the minus x. And then we've got definition of cosh, hyperbolic cosine. Hyperbolic tangent, you can sort of see the connection with trigonometric functions. There we have tan x equals sine x over cos x. Here we've got hyperbolic tangent equals hyperbolic sine divided by hyperbolic cosine. Now, a little exercise that you might like to try and we'll look at in the interactive session is an identity. If we take this expression for hyperbolic sine and square it, hyperbolic cosine, square it, and then we take cosh squared minus hyperbolic sine squared, we can show that equals 1. And we'll look at that in the interactive session. Always useful to plot a function. Well, we know what e to the x is. E to the minus x is just a reflection. So we can put those together and get the plot of hyperbolic cosine. On now to hyperbolic tangent. So hyperbolic tangent is hyperbolic sine divided by hyperbolic cosine. So we've now got several exercises for you to try. And again, we'll look at these in the interactive session. But if you get the chance to have a go at these beforehand, that would be great. So the sketch of the hyperbolic tangent as x goes from minus infinity to plus infinity. And also some identities I mentioned before. The hyperbolic cosine squared minus hyperbolic sine squared equals 1. And the derivative, working out the derivative of the hyperbolic tangent. So in order to do that, we've got to know the derivative of an exponential. We've got that sorted. And be able to use the quotient rule, which hopefully you've had some experience with as part of A-levels. If we've got one function, i.e. the e to the x minus e to the minus x, divided by another function, and we've got the quotient rule there. So then the final question is, well, why are hyperbolic functions needed for the falling ball problem? So let's go back to our picture with our force due to weight, due to gravity, and drag, the air resistance. Don't want to delve too much into physics, but Newton's second law, mass times by acceleration equals the total force. So m dv by dt is the acceleration equals the force due to gravity plus the drag, which is upwards, so mg minus kv squared. We'll quickly rearrange that. So we end up with this equation here. Now, something that you will do in the first year of a maths or an engineering degree is quite a lot on how to solve a differential equation. Now, the final exercise for you to try, which is pretty tricky, is to prove by substitution that if v is given by this result here, then that satisfies the equation, the differential equation. So we'll look at all of these aspects and what the plot of that velocity as a function of time is and how it compares to experiments. But the topics for our follow-up session, we've got proof of properties of hyperbolic functions. We've highlighted a few of those. We'll look more at the actual modelling aspect and what properties of a ball affect terminal velocity. How does the terminal velocity of a tennis ball compare to a golf ball? And the final question is, why do golf balls have dimples? So I hope you'll join me in the live lecture when hopefully I won't have this persistent cough. But I really look forward to talking to you, and I'll be able to answer hopefully any questions that you might have about what it's like to study maths, and particularly applied maths, at university. Thank you for listening.